Welcome back to Episteme. Today we'll be doing another Curiosities episode. So that just means we're going to talk about some things that are loosely related to the last paper we did, which was in the Brickin It Up episode. That was an episode about ceramics manufacturing and some of the ways that that's being done or being researched these days. We'll be talking a little bit about something that was mentioned in the paper, polymer-derived ceramics. We'll be talking about the method of heating that was used to achieve those super fast temperatures, and Hunter will be talking about some things as well. So let's do that.
I'm Hunter.
And I'm Luke, and you're listening to Episteme, a show where we explore papers in STEM fields and let you know what they're all about. So I'm going to get started today by talking about joule heating a little bit and one of the really interesting ways that it can be used. In the paper that we covered in the last episode, the researchers used carbon strips to heat ceramic discs. And one of the reasons they did this is because these carbon strips are really good at delivering heat quickly and efficiently. Another experiment that's been done using the same type of heating, but instead of using carbon strips, they use carbon nanotubes. So carbon nanotubes are exactly what they sound like. They're very, very small, nano-leveled structures that are made from carbon in tube shapes, and they're known to be very strong and are known to have interesting thermal properties and electrical properties. They're just pretty cool, a pretty cool material in general. So joule heating, as a reminder, is basically the exact same thing that a toaster does. It's the idea that you pass electricity through a conductor, and those electrons that's moving through that conductor bounce off the walls of the of whatever you're passing through, the wire or whatever, and that heats it up, and that causes heat to be generated, and that heat is transferred to the thing you're heating up. So like a toaster works this way, an oven works this way. Pretty much everything with a heating element works this way. But if you replace those wires with carbon nanotubes, you would expect that they would behave basically the same as metallic wires, where they would heat up with electric current. So these other researchers we found that were doing some work with this joule heating with carbon nanotubes, they used what's called electron thermal microscopy to observe where heat went whenever they tried to heat something up with carbon nanotubes. But they found something really interesting. They found that when they applied electric current to these carbon nanotubes, instead of heating up the nanotubes and the nanotubes heat up the substrate the nanotubes were near, the substrate heated up, but the nanotubes didn't heat up at all. So imagine how strange it would be if you were toasting something and your toast was burned, but your toaster was still cold. Or if you put a kettle on the stove top and your water started boiling, but there was no heat on the top of the stove. You can see where this would be very strange, right? So that's basically what they're seeing here on a nano level. So what the researchers think this is caused by is, instead of electricity causing thermal generation and that heat radiating to, whatever is nearby that object, instead of that being the method of thermal transfer, they think that those currents that are traveling through the nanotubes are instead just producing an electrical field, which is interacting with the electrical field of nearby objects. So it's transferring that energy still in enough to heat up the nearby objects, but it's not heating up the nanotubes themselves. So it's interesting that they were able to discover this heat transfer without using a conventional method of heating. So just to reiterate, this heating is occurring via an interaction between electronic fields versus thermal radiation. Now, it's important to note that this only really happens on a micro scale or a nano scale. They don't really see the same effect in other scenarios. So that's one of the things they're currently researching, is what other materials can we do this with, and how scalable is this, and just properties in that sense. One of the possible applications of this would be in microelectronics or computer microprocessors. These components could have an integrated heat management system with these carbon nanotubes built into them. So if you wanted to improve heat management for a processor, like for a computer chip, it could enable them to run much faster. That's kind of the limiting factor for a lot of computer chips, is they can't run faster because they get too hot and you can't move the heat away from the processor fast enough to keep up. So having this new method of heat management could be a game changer for processors and microelectronics.
Along with heat management, as Luke was talking about, the ceramics in microprocessors and in other systems in electronics is actually used as an insulator. With an electrical engineering related background, I've used semiconductors a lot in the past, but I've always wondered why ceramics are used in semiconductors, resistors, and other components within an electric system. For those that don't know what semiconductors are, they're what make most modern technologies possible. They're small devices that allow for control of electrons within them This gives people control over current in a system and many other uses to control different variables within a system. The answer to the ceramic problem is fairly simple. Ceramics resist the flow of current, and they do this by holding their atoms really tightly together, which doesn't allow for free electrons to move. This is the case for most ceramics. However, there have been some impurities within ceramic systems that allow for electrons to go through, but rather than taking this as faults, engineers have actually redesigned and changed those fault systems into their advantage in allowing for some ceramics to be conductive. Due to this, most ceramics can be used as great insulators because they prevent the loss of voltage or current in a system, along with preventing unintentional circuit bridging. However, if the right ceramic is needed, there is a way to engineer it.
So if you had a ceramic that was designed to be a good electrical conductor, it would already be a good thermal insulator. So you could combine these two characteristics that oftentimes, either they're both good insulators or they're both good conductors. You could have a thermally insulated, electrically conductive material, which is kind of a cool thought.
Yeah, very cool.
So something else that I mentioned in the paper that we didn't go into a lot of detail, but we sort of touched on, was the polymer-derived ceramics, or PDCs for short. So just to recap that, a PDC is basically a pre-ceramic polymer. So a polymer is like a plastic, more or less, which undergoes a chemical change during pyrolysis, and it turns into a reinforced ceramic composite material. So pyrolysis is basically a decomposition via extreme temperature. Usually it's in an oxygen-free, or what's known as an inert environment. During this process, hydrocarbons and water exit the material, and they leave mostly silicon-based compounds behind. So most of these polymer-derived ceramics are silicon-based as a result of that. And as mentioned in the episode, what's interesting about them is their use in additive manufacturing. So the difference here is that you're manufacturing with a filament that's eventually being, melted or cured into a final product. The difference between these filaments is that they add compounds to the filament that cure under UV light. So you have your pre-ceramic material, it's printed, cured with UV light, and then it's pyrolyzed and experiences uniform shrinkage throughout it. So you can get these really interesting dimensional characteristics. One of the applications of this type of manufacturing is you can get really interesting shapes that could be used in the aerospace industry in propulsion components, or just polymer-derived ceramics in general can be used as heat shields in the aerospace industry for all those properties we mentioned in the previous episode about their thermal resistivity and the resistance to shrinkage or property changes in extreme temperatures. So you have the ceramic for all of these reasons we've just mentioned, but then you have the added benefit of these polymers, which are typically in the form of fibers, which give the material an enhanced structure, uniformity, and density, and all those good things.
Speaking of uniformity, let's move on to talking about glass. Glass and glass ceramics have been known to be used all throughout history and have been commonly used in many ancient civilizations. One of our listeners, Apruva Kauskar, brought up an interesting fact about glass. That is that glass is neither a liquid or a solid, and that it flows, leading to buildups of glass at the bottom of windows. Looking more into this, it turns out glass is an amorphous solid. This means that it has properties of both solids and liquids. When glass is cooled, it appears to be a solid. However, it does not have a set crystalline structure like most solids, giving it properties of a liquid. Glass does actually flow, but is so slow that it would take millions of years to shift a noticeable amount. So unfortunately, glass causing windows to be bulkier at the bottom has been debunked. This can be mostly attributed to imperfect glass manufacturing processes. Glass itself is similar to a ceramic, but is not described as such until it undergoes more processing and becomes a glass ceramic. Glass is first manufactured, then it is reheated for more processing to allow for it to crystallize. Nucleation agents are usually added to help with this crystallization process. The processing of making glass ceramics turns it into a more structured solid and allows it to lean more towards the solid than the liquid state. A common application of glass ceramics is in glass stovetops. These glass stovetops take advantage of the high thermal capacity of ceramics and allow for them to actually be used to make it look good and be able to do the purpose of a stovetop. Another really common use for ceramics is in landfills. It's actually used for a more sustainable reasoning. Landfills utilize clay liners to help contain water within their systems. When used properly, this helps to prevent or limit the amount of seepage from the landfill into nearby water systems or natural features that could be harmed by waste seepage coming from the landfills. Interesting enough, most of these clay liners are around 6 millimeters thick, which is a lot thinner than I would have expected. However, the thinness of this layer is made possible by having a composite material above the clay that helps absorb the moisture. So the clay itself is a last line of defense pretty much and allows for a protective measure to help the soil that the landfills are sitting on top of.
Okay. Interesting.
Yeah. Well, that concludes all we have for the show today. We went into some interesting curiosities we had on ceramics in general and related to the paper that we just did. Thanks for listening. And if you want to hit us up on Instagram, follow us at epi.stem.
Or you can reach out to us on our email account. It is epistem.pod@gmail.com.
And as usual, if you're feeling really generous, go to our Patreon at patreon.com/epistem.
Thanks for listening.